the second lecture about blood. The title of this lecture is Blood 2, Blood Part 2. We talked about the cells of blood in the last lecture, and I mentioned leukocytes, or another name for white blood cells. They only make up less than 1% of the total blood volume, but they have an important role in their response to infection. They are the infection fighters of the body. The white blood cells leave the capillaries by a process called diapedesis. This is when they squeeze and change their shape to move out of the spaces in the capillaries and get into the surrounding tissues. There's different types of leukocytes. And you see here there's two main categories of leukocytes. There's granulocytes and agranulocytes. Granulocytes are the leukocytes, or white blood cells, that have visible granules in their cytoplasm. And agranulocytes, the prefix A in front of a word means the opposite, or it means there's no visible granules in the cytoplasm. And we'll look at the different white blood cells that are in each category. Granulocytes include the neutrophils, eosinophils, basophils. Agranulocytes include the lymphocytes and monocytes. And there's a mnemonic to help remember which of these blood cells are in the more abundance compared to those that are in least abundance. And the mnemonic is never let monkeys eat bananas. So the N stands for neutrophils. The neutrophils have there are more neutrophils than any other white blood cell. Next comes lymphocytes. Next comes monocytes. Next comes E, eosinophils, and then finally B, basophils, are the fewest number of white blood cells. This diagram shows the same thing. You can see that this is the result of the centrifuge. Well, I talked about it on the last lecture. You spin the tube, and you have the platelets and the leukocytes separate out from the erythrocytes. If you just take the leukocyte section and blow it up, the largest section here contains neutrophils, like the N in never. And the next largest segment is lymphocytes. Next largest segment is monocytes. Next largest segment is eosinophils, and the smallest amount of white blood cells is the basophils. So let's look at what these different white blood cells are indicated for. Each of them have a different function and a different purpose. The neutrophils, again, are the most numerous of the white blood cells. They're also called polymorphonuclear leukocytes, or PMNs. And again, these are part of the granulocytes. They have granules, and these granules contain hydrolytic enzymes, or defensins. These are used to destroy bacteria and other foreign invader cells in the body. The nucleus of the neutrophil has 3 to 6 lobes. Here, this example shows 3 lobes to the nucleus. These neutrophils are very phagocytic. Phagocytic means they engulf their prey, like bacteria. If you have a bacterial infection, your neutrophil count goes up high. That is the body's response to the infection to try to counteract the infection. This could be measured in the laboratory setting, and when you get an order of CBC, or complete blood count, with the differential gives a percentage of the white blood cells being neutrophils, lymphocytes, or the other types. So if you get a differential with a high neutrophil count, you're more than likely dealing with a bacterial infection. That's why it's important to know the neutrophils indicate a high bacterial infection. Next come eosinophils. Eosinophils, again, these are granulocytes. So you can see the granules in the cell. These nucleus have 2 lobes, and the purpose of this white blood cell is to attack parasitic worms. The rarest of the white blood cells is the basophils. This contains a deep purple nucleus with 1 or 2 constrictions. The granules are large, purplish black, and contain histamine. You see the granules here. The granules are very easily seen in this white blood cell. Histamine is an inflammatory chemical that acts as a vasodilator. Vasodilator means it dilates the blood vessels and it attracts white blood cells to inflamed areas. So this type of white blood cell is seen in a situation where you have inflammation of a wound, for example. There's a lot of basophils that cause other white blood cells to come in to help clean up the infection or whatever's causing the inflammation. Now we're looking at the agranulocyte. The second most numerous white blood cell is the lymphocytes. These are large, they have large dark purple circular nuclei within the rim of blue cytoplasm. See, here's the cell here. The majority of the cell is taken up by the nucleus. All that's the nucleus, and not only just rim of cytoplasm. These can be seen circulating in the blood, but they're mostly found in lymphoid tissue such as lymph nodes or the spleen. These cells are very crucial for immunity and for an immune response. The T lymphocytes and B lymphocytes. T lymphocytes are called T cells. They act against cells that are infected with virus, and they act against tumor cells. So these are geared more towards cellular defense, or defending against abnormal cells. B lymphocytes, or B cells, give rise to plasma cells, which produce antibodies. Antibodies often can fight different types of infections, such as bacterial infection or foreign body infection. And monocyte, this is the largest of the leukocytes. It's had an abundant pale blue cytoplasm and a deep, dark staining U-shaped kidney-shaped nucleus. This nucleus shape kind of reminds me of Pac-Man, and that's what this does. These are Pac-Man cells. They're macrophages. The monocytes become macrophages when they leave the circulation and enter the tissues. They become macrophages, and macrophage literally means big eater. These are cells that gobble up infected cells, tumor cells, and other cells that are abnormal and toxic to the body. This diagram just shows that all of the different white blood cells, eosinophils, basophils, neutrophils, monocytes, and lymphocytes, all come from one common ancestor, the hematopoietic stem cell. We talked about in the last lecture how the hematopoietic stem cell is basically the grandfather of all the blood cells, including the red blood cell and even the platelets. They all come from the hematopoietic stem cell. Platelets form a temporary plug that seals any tear or structural break in the blood vessels. So platelets don't really have that much to do until there's a break in the blood vessel, and the platelets stop the bleeding. They plug up the hole to stop the bleeding. They derive from the hemocytoblasts. The precursor to platelets is a large cell called the megakaryocyte. And you can see that on this previous slide here. But no, it's not on this slide. But basically, platelets are fragments of the megakaryocytes. Here's the slide I was looking for. This megakaryocyte here. Again, the hematopoietic stem cell is at the beginning, and it goes through different stages, and it gets to the megakaryocyte, and then that breaks up into smaller particles of cells called platelets. Let's look at the concept of hemostasis. Hemostasis, as the name implies, hemo meaning blood and stasis means still. So this is basically this is what happens to the body's way of stopping bleeding. If you have a cut and you bleed it first, then the blood clots up and it stops the bleeding. This is the steps that the body takes in stopping bleeding. 3 steps. Number 1, vascular spasm. Number 2, platelet plug formation. And number 3, coagulation. Let's look at these steps individually. The first step, vascular spasm. Let's say that you have here's our blood vessel with blood cells inside, and for some reason there's a cut in the blood vessel, and blood starts to leak out. Blood starts to escape through that vessel. The first thing that happens is vasoconstriction of the damaged blood cell. this blood cells constricts the muscles in the wall of the blood vessel constrict, and they constrict so that it reduces the blood flow through this particular vessel, capillary or blood vessel. With the reduced blood flow, there's going to be less blood leakage from the hole in the side of the blood vessel. Step 2 is the platelet plug formation. In a normal situation, if you don't have an injury to the blood vessel, the platelets don't stick. They just flow through and mind their own business. But whenever there's a cut in the blood vessel, it exposes collagen fibers that are in the wall of the blood vessel. These collagen fibers have a direct stimulus to the platelets. It causes the platelets to stick to the collagen fibers, and it creates a positive feedback system where there's platelets start to stick, and it causes other platelets to stick, causing other platelets to stick, and it's a positive feedback system. Most of the time in the body, we have a negative feedback system for hemostasis, or for hemostasis, but in this case, we have a positive feedback cycle. Here it illustrates the tear. The tear is quickly plugged up by these platelets. The platelets stick, and more platelets bring on more platelets, and it just keeps adding to it. Stops up the hole and blocks the hole and stops the bleeding. But that platelet plug is basically a temporary plug. What you need is a more substantial, stronger plug to keep the hole from getting larger. And when the vasoconstriction stops, then you have more blood flow. So you need to have a way to contain that blood flow, and that's where coagulation forms. Coagulation is when fibrin, which are protein cells within the proteins within the blood, form a mesh, a strong mesh that traps red blood cells and platelets, and forms a clot. It's basically, if the platelets were if platelets are like a temporary hole plug, the coagulation is like concrete. It's a more permanent. It's a more permanent way of stopping the blood flow, and it's more permanent so that by the time it dissolves, and the blood vessel has been repaired, and the hole is no longer. The process of coagulation involves reinforcement of the platelet plug with a cross-linked fibrous mesh. This produces a very strong, very strong plug, if you will, for the hole in the blood vessel. There's a series of plasma proteins and clotting factors. It's a very complicated sequence of events that occurs. But the end result of all of the coagulation process is the development of this fibrin mesh. This is an electron microscope view of fibrin mesh. It's like a spider web, basically, full of all these fibers, and they trap red blood cells and platelets and white blood cells inside. And this is the concrete that plugs up the hole. This is a fibrin mesh. All right, we'll shift gears a little bit and talk about transfusions. This can get a little tricky, so I'll try to explain it as we go along. But as you know, we can get transfusion of blood. Whole blood transfusion is transfusion of the whole blood, which were red blood cells, plasma, everything in the blood. If there's rapid blood loss and it's substantial, that's when a whole blood transfusion is indicated. You can also transfuse just the red cells. So they have a process where they can remove the plasma and the white blood cells and just transfuse red blood cells. It's important to make sure the blood that you're getting transfused with is compatible with your own blood, because incompatibility can be very fatal. We want to talk about antigens and antibodies. An antigen is on the surface of all cells. The plasma membranes of all cells have specific markers on their external surface which identify that cell as being unique from others. It also identifies that cell as coming from your own body versus coming from another source that's foreign to your body. The antigens are the parts of the cell that are recognized by the immune system so that it can tell one cell apart from another. The term antigen means antibody generating. Okay, antibodies are the parts of the immune system that are directed towards the antigens, and once an antibody attaches to an antigen, that cell is marked for destruction. Substances can mobilize adaptive defenses and provoke an immune response. Exposure to antigens causes the immune system to form antibodies to the antigens. And again, when the antibodies form in response to the antigen, they lock on the antigen, and then that cell is set up for destruction. Let's talk about the blood transfusion specifically. The red blood cells have one of four combinations of antigens. Okay, they can either have antigen A or antigen B, or they can have both antigen A and antigen B, or they can have neither antigen A or antigen B. These are antigens that are found in the different blood cells. These are you're born with one of these four types of antigens of A and B. Now, the plasma in our blood contains one of four combinations of antibodies. You have either anti-A antibodies or anti-B antibodies, or you have both anti-A and anti-B antibodies, or you have neither anti-A or anti-B antibodies. Again, this is something you're born with. You're born with one of these four conditions. When an antigen and an antibody get together, they agglutinate or clump together, and then they're set up for destruction. Once they clump together, they're picked off by the spleen and by the lymphatic system, and they're destroyed and eliminated. So let's look at this table. This table is complex, but it describes the different blood types and what makes a blood type. The first column we're looking at here, the erythrocytes are the red blood cells, the plasma, and the blood type. Look at starting at the bottom of the table. Type A blood. What makes blood type A versus type B blood? Type A blood has antigen A antigens on the red blood cells, but floating through the plasma of the blood, there's anti-B antibodies floating in the plasma. Notice these anti-B antibodies do not interact with antigen A antigens. If they did, it would be a self-destruct for the red blood cells. But since your body recognizes your own blood cells as your own, they're not going to want to destroy it. So you have antigen A and anti-B antibodies is what makes up a type A blood type. Type B has a similar situation. Type B blood type, you have antigen B antigens on your own red blood cells, and floating in your own plasma you have anti-A antibodies. That's what makes up a type B blood or B type blood. Other blood type is AB blood. AB is kind of a combination of the other two. In AB blood, you have antigens A and antigens B. Both antigens are on your red blood cells. But in your plasma, there's neither anti-A nor anti-B antibodies floating in the plasma. The fourth type is type O. Type O is sort of the opposite of type AB. In the type O, there's neither antigen A or antigen B on the red blood cell, but within the plasma there's both anti-A and anti-B antibodies. So each blood type has a certain pattern of antigen and a certain pattern of antibodies. And you just remember that there's whatever antigen they have in a normal situation, they have the opposite anti-antibodies. So if they have antigen A, they have anti-B antibodies floating in the plasma. If they have antigen B on the red blood cells, they have anti-A antibodies floating in the plasma. This says the same thing, but just in paragraph form. You can read this, so I'm not going to read this to you. I'll leave it on the side. I don't know if you can read it. If anytime you need to stop the slide, if I go to fast, stop it so you can read it. Basically, this just describes what I just told you on the previous slide. If any of a blood type is mixed with the same blood type, there's no clumping there's no agglutination that occurs because there's no antigen antibody reaction. And that's what you want to see. That's why when you're typing for blood type, if you have A positive blood, they're looking to try to transfuse with A positive blood, so there's no interaction between the transfused blood and your own blood. These same conditions that are on the last slide. I just put in there to remind you. Let's say you have a person with type A blood, and by mistake they're given type B blood, type B red blood cells. What's going to be the result of that? Well, in type A blood, remember type A blood has type A antigens on the red blood cell, but anti-B antibodies in the plasma. Type B blood has type B antigens on the red blood cell, but anti-A antibodies in the plasma. These anti-A antibodies in the transfused blood is going to interact with the antigen A in your own blood. Or if you're just given red blood cells without the plasma, then your own anti-B antibodies are going to interact with type B antigen for the transfused red blood cells. The bottom line is when you're given two different types of blood, it's going to result in the antigen and antibody complex agglutinating together, and they lock together, and that's going to cause destruction of the red blood cells. That's not a good thing. Sorry about the phone call. Okay, let's look at another situation. Again, this same conditions on the top here. This is the same as on the other side, just to remind you of what blood type has what type of antigens and what type of antibodies. If somebody with AB blood is given any other blood type, what's going to happen? Well, AB blood, remember, has antigen A and antigen B antigens on the red blood cell, but within the plasma there's no anti-B, there's no anti-A antibodies within the plasma, so they don't have either anti-A or anti-B antibodies floating in the plasma. Since there's no antibodies floating in the plasma, it cannot react to the blood that has been given. It cannot react to the antigens of the transfused blood. So therefore, somebody with type AB blood can be given any other type of blood type safely. That's why AB blood is known as the universal recipient blood. It can receive any type of blood type without complications. Now, the last case, if type O blood, remember type O blood, it says it has neither A nor B antigens in the red blood cell, but has both anti-A and anti-B antibodies in the plasma. If you have type O blood and you're given any other blood type, there's no clumping occur there because you don't have any antigens on your red blood cells to interact with any antibodies that will be floating around in the recipient's plasma. That's why type O blood is a universal donor, because it can take any kind of blood without transfusion complication. Since it doesn't have the antibodies, either anti-A or anti-B antibodies, it's not going to react to the antigens. So that's why type O is a universal donor. And a quick way to remember that, donor has two O's in it. Type O is universal donor. Type O, and then donor has two O's in it. This kind of illustrates the same thing. It looks at, like in this case, AB blood. If you have AB blood, you have A antigens and B antigens, no anti-A or anti-B antibodies. It can receive, this person can receive a transfusion of A blood, B blood, AB blood, or O blood. Remember, AB blood is a universal recipient blood, so it can receive any type of blood. Type B blood, the second line, has B antigens and has anti-A antibodies, and therefore it can receive B blood, type B blood, or type O blood, because O is the universal donor, so it can go to any blood type. Type A blood, again the same situation. You have type A antigens and anti-B antibodies. So somebody with type A blood can only receive blood that is type A or type O. Now the last category is type O blood. It has no it has no A antigens or no B antigens, but it does have anti-B antibodies and does have anti-A antibodies. Since there's no antigens in this blood, it's not going to he can only receive type O blood. That's why it's called a universal donor. This could be given to any. This blood can be given to any person with any type of blood type, because it does not have antigens in its blood that's going to react to the antibodies in the recipient's plasma. So therefore, it's a universal donor blood. I'm talking about A and B blood and AB blood, but when you get your blood type, it's usually AB positive or AB negative. Well, there's a positive and negative. The positive negative refers to the Rh antigen or Rh factor. Rh positive blood has Rh antigens. Rh negative blood does not have Rh antigens. Let's say you have a person is Rh negative and they're exposed to Rh positive blood. Then for the first time their blood is seized, this Rh positive blood in their blood in the blood supply is recognized as foreign, so antibodies to the Rh antigen are formed. If the Rh negative person is exposed to Rh positive blood a second time, then the antibodies that were previously formed to the Rh positive blood come out in more abundance. They make the second time around they have a much stronger immune response. And so the second time they're exposed to the Rh positive blood, they form an antigen antibody reaction and clump the cells together, and then they're marked for destruction. If an Rh positive person, the first case was Rh negative person, but here we'll say Rh positive person is exposed to Rh negative, no antibodies are formed since there's no exposure to the Rh antigen. Rh negative means there's no Rh antigen in there, so there's not going to be a reaction to the Rh antigen because there's no Rh antigen in that blood. So a person that's Rh positive can receive both Rh positive and Rh negative blood. A person that's Rh negative, however, can only receive Rh negative blood, because when they receive Rh positive blood, like in this situation on the top, antibodies to the Rh antigen are formed. This is a kind of visual diagram to illustrate that. So we have a drop of blood here, and we don't know what type it is. We want to do a type test the type of blood here. We have A blood, B blood, AB blood, or O blood. So we put it in these test tubes, and these test tubes have different antigens in the test tube. There's antigen A, antigen B, and the Rh antigen. So when you mix this blood in with each of these test tubes, like in this case, this blood mixes with A, and it clumps together and it kind of settles down. Since it clumps together, that means antigen A has had to react to anti-A antigen from anti-A antibodies. Since it reacts with antigen A, and this is a blood type, this is A blood type, the blood type A. It does not react in blood to blood B, so it's not blood type B, and there's no reaction to the Rh factor, so this means it's a negative, Rh negative. So this blood type would be A negative. It has a positive reaction to A, and no reaction to B, or no reaction to the Rh factor, so this has to be Rh negative, to be A negative blood. This is another example. This is let's see. That's the same example. This is Rh negative blood. Now, if you want to try to decide what kind of blood this person can receive on transfusion, you could either give them A negative blood or O negative blood, because their blood type is A negative, so you give them A negative. You always give them the same blood type that they have, or if you're in a pinch and you don't have A negative blood, but you have some O negative blood, O negative blood can be given in transfusion to this person. O blood is the universal donor, and negative means negative RH factor can be given to somebody with negative RH factor because no antibodies are going to be formed. Here's another example. Here's unknown blood, and we're going to test it, see what blood type it is. When we put in the antigen A tube, nothing happens. Put in the antigen B tube, they clump together. So that means it has anti-B, or it means it has B antigen in this blood. We put in the RH factor, it clumps together, so it means it's RH positive here. So this blood type will be B positive. It reacts to B and it reacts to the RH, so it's B positive. If you're trying to decide what kind of transfusion to give this person, certainly you can give them B positive blood. But they can also receive somebody's blood that's B negative, O positive, or O negative. O is the universal donor, remember, so O can be given to anyone. And since there's a negative RH factor in the recipient, they can get RH factor positive or RH negative because they don't have the ability to make antibodies to the RH factor anyway. The RH gets its name from rhesus monkeys. Originally it was described in rhesus monkey. RH gives the antigen the positive or negative in blood type. Unlike the ABO antibodies, anti-RH antibodies does not spontaneously form in RH negative individuals. It only forms when there's exposure to RH positive blood. For example, an RH negative mother is carrying an RH positive fetus, and during the birth, the blood of the fetus mixes with the mother's blood, and she can then mount an antibody response to the RH positive blood. So if you have the RH negative mother is pregnant for the first time, and her fetus has RH positive blood, then the RH negative mom is exposed to RH positive blood during the delivery of the first baby. The first baby's healthy, okay, because it's only after the baby's gestation time and during the birth does the mother get exposure to the RH positive blood. But once she's exposed to RH positive blood, then her blood starts to make antibodies to the RH factor. She starts synthesizing anti-RH antibodies. Then let's say that RH negative mother gets pregnant again with another RH positive baby. Then she had antibodies that were created during the first exposure to the RH positive blood. These antibodies then are produced more rapidly and in larger quantities before, because it's the second exposure. They cross the placenta and they can destroy the red blood cells of the RH positive baby. This is a condition called erythroblastosis fetalis, or hemolytic disease of the newborn. This could be devastating for the baby. The baby can become anemic and hypoxic and can cause brain damage or even death of the baby. So how is this avoided, or how is this treated? There's a serum called RhoGAM. RhoGAM is a serum that contains anti-RH antibodies. If you have the RH negative mother and she has a RH positive child, shortly before or after birth of the child, she's given this RhoGAM, which is full of anti-RH antibodies. These anti-RH antibodies that are in the RhoGAM clump with RH antigens that come from the baby during exposure to the blood. So they basically they link up with these RH antigens from the baby's blood, so that before the mom's blood has a chance to react and form antibodies to that. These RH antigens are then destroyed, which prevents the mother's blood from producing anti-RH antibodies. If no anti-RH antibodies are made, then erythroblastosis fetalis is avoided. Let's say say they didn't get good prenatal care and it wasn't recognized that there was a mismatch between the blood of the mother and the blood of the baby, and RhoGAM was not given during the first pregnancy. Sometimes they require a transfusion before birth to try to put more red erythrocytes in there to make it available for oxygen transport. Again, you want to try to avoid the hypoxia that occurs with low amounts of red blood cells. And then after the birth of the baby, The baby may receive 1 or 2 exchange transfusions to try to replace the baby's Rh positive blood with Rh negative blood. Rh negative blood, that way it won't react to the antibodies that the mother formed against the Rh positive blood. This transfused blood breaks down after 6 weeks, and then the baby's own Rh positive blood can be replaced and grow back. Hopefully that made some sense. I know it's kind of a complicated subject matter, but you can rewind this video and watch it again, or refer to the chapter in the book regarding this, and may explain it a little bit better there.